Okay, welcome back everybody. In this video we're going to talk about, continue our discussion of the implications of differentiability, and we're going to talk a little bit about local linearity. We left off here with the implications of differentiability at the end of the last video, and so let's look at the first implication of differentiability, and that implication is that differentiability implies local linearity. So differentiable functions possess what's known as local linearity, okay, which means that functions that are differentiable at some value a resemble their own tangent line close to that value of a. So very close to the particular point where a equals 2 in this investigation, you'll see that the curve begins to look like a line very close to a. Specifically, it begins to look like its own tangent line. Alright, so now we're going to do a little investigation of this function y equals x sine of 3x, where a is equal to 2. And I'm going to go ahead and do that on my graphing calculator. I'm going to take the function y equals x times the sine of 3x. And we'll go to the standard window. And you see this is a pretty crazy curve. But we're specifically interested in the behavior around where a is equal to 2. And so I'm going to zoom in on this. And I'm going to center it. Oops. Guess I can't do that. I'm going to zoom in on this. And I'm going to center it pretty close to where x equals 2. And you see this curve here is starting to look a little bit more like a line. And I'm going to zoom in again. I'm actually going to use the zoom box command and build a box around where x equals 2. And x equals 2 in this neighborhood. Now I want to make sure I capture the curve around 2. I'm going to zoom in again. And you see that, you know, when we're close to 2, which is just a little bit to the left of our cursor, this is already beginning to look a lot like a line. Okay? Now I'm going to go back to my standard window. And I'm going to graph on top of this the tangent line, which I took the time to find. I didn't want to do that on camera because taking that derivative with the limit of a difference quotient would have taken me probably more time than I have to shoot this video. And I'm going to make the graph of y too thick so that I can see it in contrast to the original. Where are you? There you are. Alright. And if we zoom in on this, close to 2, we can see the original curve, and we'll also see the tangent line. There it is. And you can see that the curve as we get close to that, very close to where x is 2, really begins to resemble the tangent line. And I'll box this in quick. Down to too far over here. But if I zoom in on that, you see here's the curve that you see, and then there's the tangent line. And as we get closer and closer to 2, where you see those two touching, you see that the curve and the line almost overlap with one another. And that's what local linearity means. The function behaves like a line close to any particular point. It looks a lot like its tangent line. Alright, enough about that. Next implication of differentiability is that differentiability implies continuity. So if we know a function is has a derivative at x equals a, that means that the function has to be continuous at x equals a. The converse of this is not true. Just because something is continuous doesn't mean it's differentiable. We saw that earlier. We could have a function that looked like this, where we've got a little cusp point here. This function is continuous but not differentiable at this particular point. However, if we know that a function is differentiable everywhere, that means that it has to be continuous everywhere. And this comes up for you a lot in like AP exam free response questions, where you'll be told that a function is differentiable, and you should understand that one of the implications of that is that it has to be continuous, and therefore you can use everything you know about continuity in that problem. Okay? Third implication of differentiability is the intermediate value theorem for derivatives. The intermediate value theorem for derivatives says that if we have a and b being any 2 points in an interval, when the function is differentiable, then the derivative has to take on every value between f prime of a and f prime of b. So if we know that we have these 2 points in an interval, and the derivative at one of them is 2, and the derivative at the other one is -1, then every point in that interval, the derivative has to meet every value between 2 and -1 in that interval at some point in time. Okay? Alright. Last example related to this lesson, we're going to determine the values of a and b that make the following function differentiable everywhere, and we're going to use bullet point 2 up here. We're trying to show where this is differentiable, and first of all, realize that each individual branch of the piecewise function is continuous, and it's also differentiable. The x squared plus 5 is a parabola, which is a smooth curve. Ax plus b is a line, which is a smooth curve. So they're both differentiable. So the place where we're really concerned is at x equals 1. And in order for it to be differentiable everywhere, that means that the derivatives must be the same at 1, and also the function must be continuous at x equals 1. So first off, since it's continuous, that means that the limit as x approaches 1 from the left of x squared plus 5 has to be equal to the limit as x approaches 1 from the right of ax plus b. And we can find each of these limits individually via substitution, and so we get the equation that 6 is equal to a plus b. So since it's continuous, that's true. Now, in order to show that it's differentiable, I need both of these derivatives. So I'm going to find both of these derivatives. I'll find the first one, limit as h goes to 0 of x plus h quantity squared plus 5 minus x squared plus 5 all over h, hustle here, is limit as h goes to 0 of x squared plus 2x plus 2xh plus h squared plus 5 minus x squared minus 5 all over h. Cancel, 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 cancel. That's the limit as h goes to 0 of h times the quantity 2x plus h all over h. So the limit as h goes to 0 of 2x plus h. And so the derivative of the top piece is 2x. And so f prime of 1 for the top piece is going to be 2. I do the same thing with the ax plus b. I find the derivative of it, backing myself into a corner here with space. So the limit as h goes to 0 of a times x plus h plus b minus ax plus b over h. That's the limit as h goes to 0 of ax plus ah plus b minus ax minus b over h. A lot of things canceling here. The ax and the minus ax, the b and the minus b. And so this is the limit as h goes to 0 of ah over h, which is just canceling the h's from both. And so the value of the derivative at x equals 1 for that piece is going to be a. And so these two things need to be equal to one another. This and this. And so we also get the relationship that a equals 2 from the requirement of differentiability. And now we have two equations that represent the situation that makes this true. By solving this system of equations, I can find that b equals 4, and therefore the values of a and b that make this function differentiable everywhere are a equals 2 and b equals 4. Alright, that's the end of this lesson and the end of this video. Hope you guys have a great rest of your day, and see you next time.